Hi there. My name is Dmitry Kamenko. I'm a pre-sale engineer here at StarWind, and I would just like to confirm that you can hear me and see my screen well. Would it be possible for you to see this message in the chat? So while we're waiting for the chat message, let's just give it a couple more minutes for all the attendees to join our webinar. Okay, great. So we've just received a confirmation about sound quality and video quality. Now let's just go ahead and begin our presentation today. Now, today's tap room will be quite informative since we will not only look into the best practices when it comes to measuring your storage performance, but we will as well look at in depth into the architecture of data storage. On the other hand, we will demonstrate how it will be possible to calculate the estimated amount of IOPS at the time of designing your storage system. The best part about it is you'll be able to witness the process in real time. Beforehand, I would like to mention that I have just began the benchmarking process before starting this webinar, and it should be complete by the time we finish. So we'll access the environment, which will have the complete results. Now, in order for me to keep my word, let's go ahead and access the test environment previously configured to be used. Due to the time-taking process, I have once again began the test beforehand. So let's make it clear, the process of investing into a solution I'll be able to withstand the test of time is not easy. Sometimes to make the right decision takes a great amount of research as well as heaps of trial and error in the process. And today, I will make it my goal to safeguard you through that process, discuss the meaningful differences in how storage products perform when you put them to the test, and make sure to save you some money in the process. Now, our own experience is that there are big differences in how a given hardware configuration will perform. It greatly depends on the type of software, hardware stack you're planning on using. With all that said, I would like to discuss and demonstrate the process of testing the storage performance of your virtualized infrastructure for you to get a good 360 perspective what to look out in the process of purchasing or implementing or configuring a similar solution. Before I go into the details, I can never stress enough the possibility of bottlenecks occurring in the worst possible moment. The performance of a system has four major areas: memory, speed or capacity, processing power, network bandwidth, and disk. So every system is limited to one of these areas at any given time. I just hope that your system isn't hitting one of the current bottlenecks. Performance tuning is simply the art of trying to remove each bottleneck just like a simple point of failure. The most important aspect which we will need to consider when testing a highly available storage device is that HA performance depends directly on your network and disks. Therefore, it is essential to ensure that SAN is configured properly before it is put to good use. Before we begin the testing process, there are several things that we need to acknowledge and consider when testing your performance. And the first one is storage type. Now, when it comes to hard disks, the random performance is one of the key limitations of hard disks and something that SSD would excel at. Now, the hard disk manufacturers tend to merely post average latency statistics as an indicator of random performance, while SSD vendors love to flaunt their amazing 4K random IOPS figures. Both of these metrics are important, and we determine the performance of random reads, writes, and mixed workloads of every HDD with both 4K and 8K file sizes. 4 kilobyte random workloads represent one of the hardest types of file access any storage solution, and also enables comparison with the key metrics used to determine the performance of an SSD. Many enterprise applications are heavily dependent on 8K random performance, and we include these measurements to highlight the performance trends found in many enterprise applications. Since most of the actual disk access for most production systems is small IOs randomly spread over the disks, the most critical factors will be to get as many IOPS as possible with a low average latency. This would mean that for a single disk, we would want to minimize the rotational delay by having as high RPM as we can, preferably 15K RPM for important servers, and minimize the seek delay when the disk head is moving into position by selecting disks with a low average seek time. Also known as Tier 1, these 10Ks and 15K RPM SAS drives provide the online enterprise performance and availability needed for mission-critical applications. Now, when it comes to SSDs, unlike hard drives, flash-based storage products display tremendous performance differentiation, even among models designed to compete with the same class. Now, the SSD technology has been disruptive to the established norms of enterprise storage, and flash-based storage devices present a unique set of metrics and characteristics that require analysis during the process of implementation. Performance of any storage device varies depending upon the end application, but flash-based storage increases the performance delta. Now, the sequential performance is increasingly relevant as more applications turn to SSDs for random workloads. Various caching and tiering mechanisms are also preferred flash deployment models. These techniques leverage the inherent random workload strength of SSDs to catch or coalesce random data and then sequentially pass data down to spindle tiers. This boosts performance by tailoring the data for the underlying rotating media. Data is additionally streamed to the other direction to the SSD tier when it is promoted to accelerated status, and the data is written sequentially to reduce wear on the flash media. Now, there's quite some differences in between the SSDs, and some of them are SLCs and the MOCs. Now, SOC stands for a single level cell, and the reference is the number of information bits that can be stored in each cell of flash memory. For SOC, this is 1 bit per cell. Now, when it comes to MOCs, MOC stands for multi-level cell and can store multiple bits of information per cell. SOC-based flash has a write endurance capability roughly 10 times of what MOC flash is capable of. However, it should be recognized that SSD performance changes over time. There is a period between fresh out the box and the steady state period where there is a transition period. Normalized IOPS performance, depending upon the type of memories, multi-level cell structure, will actually do a step function negatively from a peak FOB IOPS figure to the steady state IOPS measurement. When developing a level of performance matrix, the measurements will depend upon the time of I/O requests. The influencing metrics include whether the SSD access is sequential or random in nature and varies based upon the size of the blocks, the read-write workload, as exemplified from the previous comparison, and how the I/O access blocks are physically arranged on the media itself, known as a block alignment. Now, when it comes to RAID, there's also some differentiations here. There's a software and the hardware RAID, and other means of aggregating drives behind a single entity, only excavate variability. The speed of the RAID array is only as fast as the slowest member. Thus, an errant I/O from one drive slows the speed of the entire array in most scenarios. Number of errant I/O multiplies as drives are added to the array due to the simple fact that more drives are individually generating errant I/Os. Writing data to a RAID set or flash drive is often subsequently slower than reading that data back. Fortunately, most applications read more than they write. Therefore, most benchmarks include a mix of read and write operations, often skewed toward the former. We have theoretical models to predict IOPS of an application requires or that can be sustained by a RAID set. The theoretical performance of a given RAID level is often expressed as a write penalty, since parity RAID tends to slow writes down and reads. Now, another thing to keep in mind is that most enterprise systems include cache that accelerates I/O and tends to upset assumptions based on theoretical IOPS and RAID levels because cache equalizes the and accelerates performance. Now, when it comes to IOPS, to calculate the actual IOPS for given disks, the following information is required, such as the average latency and the average seek time. Now, when calculating the maximum write IOPS, is a slightly different matter. With respect to RAID arrays suffer a write penalty. The type of RAID array determines the severity of the write penalty. This penalty is a result of the redundancy that the RAID provides. The array necessarily has to write the data to multiple disks locations to ensure data integrity. Now, when it comes to calculating the maximum read IOPS for the RAID array, it's quite simple. You would need to multiply the number of disks in the array by the maximum IOPS per disk. Now, simply calculating the maximum read and write IOPS for an existing or future RAID array is not enough. To ensure consistent and sustained performance, the system architect needs to provide the performance requirements for a system to determine the best disk solution. The minimum required IOPS must be determined so that the proper number and speed of disks can be purchased. Now, every I/O request occurs at the same speed and latency with little to no variability. Unfortunately, all storage devices provide variable performance during operation. SSD and other flash-based products can feature wider performance variation in comparison to standard HDDs, which was actually presented in the previous slide. Differing performance consistency can be traced back to controllers, firmware, NAND, error control algorithms, internal management techniques, and over-provisioning. Some types of data, such as archival and code data, have more relaxed latency requirements. However, latency is the most important measurement for the majority of workloads. In reality, every storage device provides a wide description of variable latency while under load, even when aggregated into RAID arrays. The problem is that popular performance testing tools need a lot of scripting and automation to stimulate that kind of environment. Precious times get spent making things run versus getting results. Now, another thing to take into account would be the bandwidth and output. I've put together a diagram here to examine that for you. So as an example, we would use a water drip going through 3 pipe sections from A to B to represent a transaction. A pipe section can be regarded as either contain a process that is part of the transaction or the resource that is used by the process. The system goes through 6 phases where at each the flow rate or through output is decreased, then increased. The elapsed time for the data to travel from point A to point B is the response time or latency of its transition. So for all 6 phases through output, there will be corresponding value for latency. While it's true that latency is still an important network performance indicator, latency alone is a measure of application performance, which can often be misleading. Today, it's possible for a network link with a latency of, say, 100 milliseconds to deliver a better end-user experience than a network link with a latency of 80 milliseconds. It's no less important for all the previous points testing a hyperconverged storage product. It's the same as testing a traditional array. Now, when it comes to hyperconverged clusters, which are mainly busy with environments where there are hundreds of VMs, all with their own storage workloads, for which the performance data without accompanying latency measurements can be considered useless. The goal of every storage solution is to deliver consistent and predictable latency. Unfortunately, this isn't always the case. Metrics like maximum latency and only quantify the single worst I/O during the measurement window. This can be misinforming since the view of an otherwise excellent storage device can be obscured by a single I/O which went astray. Some types of data, such as archival and cold data, have more lax latency requirements. However, latency is the most important measurement for the majority of workloads, which in reality, once again, every storage device provides a wide distribution of variable latency while under load, even when aggregated into RAID arrays. While it's true that latency is still an important network performance indicator, latency alone as a measure of application performance can often be misleading. Once again, let's say if we have a latency of 100 milliseconds to deliver a better user end experience, a network link with a latency of 80 milliseconds. Now, what I wanted to do now is I wanted to access the environment which I have previously configured, and go ahead and demonstrate you the StarWind Storage Test tool. Let me just go ahead and get that up and running. What we've done here is we've created a StarWind Storage Test tool, which is a powerful tool that was designed to provide you with a simple means of assessing and comparing the read and write performance of your SSD or HDD and comparing it to your highly available fault-tolerant storage. Now, running a similar test by using standard tools, for example, VDBench, FIO, IOmeter, or anything else, usually means a lot of scripted setup and a lot of data gathering, as well as, once again, the amount of time that is spent for making things run. Now, the environment in which we'll be testing the storage performance on consists of two commodity servers. Oops, sorry. Two commodity servers. One second, let me just go ahead and review that and that slideshow. Both of them are based on a chassis which is able to contain up to 16 2.5-inch slots, contain two Intel Xeon E5 multi-core processors, have Intel network adapters for management, and Mellanox completely dedicated to storage synchronization and processing the client's traffic. They are based on a 1 gigabit RAID controller, have 128 gigabytes of RAM, 16 4 terabyte 7.2K spindle drives, which are NOSAS, 20 gigabits and 512 native, and they are configured in RAID 10. So just to let you know, I have StarWind HA device configured, and these two servers are part of the cluster. The StarWind device is locally available to the partner host on both ends. And just to briefly describe you the StarWind Storage Test tool, it's made quite simple. What we would need to do is we would firstly need to select the HA volume, then we would select the volume which will be used in order to compare, specify the test run duration, the warm-up time, which is mainly used for time that it would take to rotate the spindle drives in order to provide a more precise result, the size of the test file. Once again, we have selected 35 gigabytes in order to maximally utilize the volume, of the HA device, and number of threads, which is actually a system with a single processor generally implements multi-threading by time slicing. So the central processing unit switches between different software threads, and the number of I/O queues which we'll be using is equal to 8, and the number of I/Os is equal to 8 also. Those are some variables that are auto-defined by our tool. Now, the patterns which we'll be testing today are 4K and 64K. And the affinity stream, which we have pre-configured, is a value that is once again automatically specified based on the amount of logical processors allocated or available to the operating system instance. Now, once again, we have already pre-ran the performance test and it should be available to us right here. Let me just go ahead and open that, and that actually will provide us with an example of the performance for the storage which we selected. As you can see here on the first disk, which is the local storage, we have an estimate of 1,590 IOPS with a throughput of 22 megabits, latency of 22, and the CPU load of less than 1%. Now, the second disk, which is the HA disk created with the assistance of StarWind, shows the improvement of IOPS when it comes to random testing patterns. And once again, it does also show an improvement of sequential testing patterns. Now, when we look at the comparison, it's quite evident to see that the HA device has provided us with an increase of random read patterns, as well as the megabyte throughput, the latency, and a load on the CPU in order to improve the performance of the underlying storage, as well as it provided us with an increase of sequential reads, as well as writes in 64K block size. Now, that's that for the demonstration. Feel free to address any other questions which you may have. Just get to the last one. There we go. Okay, so now we have the first question. IOPS, bandwidth, latency, or a mix. When you set up your testing, you'll be trading off between different priorities. Now, when it comes to transactional virtualized environments, usually we optimize latency and IOPS. Now, decision support and file access environments usually optimize bandwidth, and the test and development is usually a mix of both. Okay, so we have another question. How can I get this magic tool? This tool can be downloaded from our website. Okay, another question. What would be the best practice for block sizes when testing? Now, the best practice for the interpretation of your results will be testing at 3 or more than 2. In general, different block sizes. So for example, 4K, 32K, 64 you can do, or 128K would also be an option. Now, random profiles for smaller blocks, sequential profiles for larger blocks as well. Now we have another question. What NICs have you used for connecting the nodes? We've used 10 gigabit NICs. Okay, so I would like to thank everyone for joining the webinar today, and I hope you are able of squeezing the maximum amount of your performance juice out of your redundant storage. Thank you. Goodbye.